We can see from the work done by McAdam just how nonlinear the chromaticity diagram was from the standpoint of perception. We need a space that uses the same basic tri-stimulus concept, but is much more linear from the standpoint of perception. We can think of trying to plot the chromaticity diagram on a rubber blanket and somehow distorting this rubber blanket mathematically to convert it to a circle. In 1976, the CIE says we have a space that's much more linear. It's called the CIE L star, A star, B star space. The stars were added to differentiate this space from other LAB spaces. For the rest of this tape, when we talk about the CIE L star, A star, B star space, we're going to refer to it just as the LAB space.
It's helpful to think of color space in terms of a cylinder. If we look at a cross-section of this cylinder, we can see that hue is arranged in a continuous scale from red to violet. Chroma increases outward from the center, or neutral point, starting with gray and gradually increasing in saturation. The lightness scale is arranged from top to bottom. Lightness forms the third dimension of this color space. The lightness value of a color is referred to as L. A black will have a low L value, while a white will have a high L value. CLAB is one of the most uniform color spaces. For the purpose of illustration, we'll work with a cross-section of this cylinder as if it were CLAB space. This space is divided by two axes, which intersect at the gray-neutral area in the center. A is the red-green axis, with red on the positive side and green on the negative side. B is the yellow-blue axis, with yellow on the positive end and blue on the negative end. A sample is plotted in this space by means of its L, A, and B coordinates. These coordinates are determined through equations which start with the color's tri-stimulus values X, Y, and Z. This sample has a lightness, or L value, of 55. Its A value is 50, and its B value is 30. A line is drawn from the intersection of the A and B axes through the point representing the sample. The longer the line, the higher the chroma of the color. This sample is a high chroma orange. In this example, a second sample has the same L value. Its A value is 30, and its B value is 50. When plotted, the color is positioned closer to the B axis, which means that this orange is more yellow than the other sample. Since both samples have positive A and B values, we can tell by the numbers that both samples are positioned between the positive A, or red axis, and the positive B, or yellow axis. Therefore, both samples plot in the quadrant between the red and yellow axes. Here we have a standard and a batch. The standard has an A value of -30. Its B value is -40. The batch has an A value of -50 and a B value of -30. The negative values for both A and B mean that both samples are plotted between the negative A and B axes, the green and blue axes. We can see that both samples are of a bluish-green hue, and that the batch is less blue than the standard. Once again, the numbers provide us with information about the colors and the relationship between them. If we look at the L values, we can see that the L value for the standard is 35. The L value for the batch is 45. This means that the standard and the batch also differ in terms of lightness. By shifting our perspective on the LAB space, we can see that samples with different L values will be positioned on different levels or planes in LAB space. We can now measure the total color difference between a standard and a batch by calculating the distance between the samples in all three dimensions. This calculation, which determines the difference between the samples in terms of LAB, is performed by computer. The difference between the L value for the standard, 35, and the L value for the batch, 45, is calculated to determine the total difference in lightness between the two. This lightness difference is called delta L and is represented by the symbol DL star. Here the value for delta L is 10. The difference between the A values is also calculated to determine the total difference in redness-greenness. This difference is called delta A and is represented by the symbol dA star. In this example, the value for delta A is -20. This calculation is repeated using the B values of the standard and batch to determine the total difference between the two in terms of yellow-blueness. This difference is called delta B and is represented as dB star. Here the value for delta B is 10. A color difference equation uses delta L, delta A, and delta B to calculate the total color difference between the standard and the batch. This total color difference is called delta E and is represented by the symbol dE star. Delta E represents a single value for the total color difference between a standard and a batch. If we attempt to use delta E to establish a single tolerance or set of limits for color approval, however, it presents certain problems.
When we use this concept of delta E for our industrial tolerance work, we find that in many cases the delta E agrees with our visual assessment. But we don't have to work too hard to find situations where the equation would indicate that we do not ship a batch, when in fact when we look at it we feel that it is acceptable. In other situations we'll have an indication from the equation that a batch is acceptable when we'd say we'd never ship that. So we have the problem that our visual assessment does not always agree with the delta E calculation. I emphasize that the difference or the problem is with the equation. The equation doesn't always represent our visual assessment. So we have to find some way of improving the equation to represent what we see.
We can begin to understand these problems by examining the results of visual evaluations made by a group of British textile dyers. Each point represents the position of standard colors made by the dyers. Actual batches that were judged to be visibly acceptable for customer approval were then plotted. The results of these visual evaluations formed ellipses. The smaller dimension within each ellipse shows the difference in hue that was judged to be visually acceptable. The larger dimension shows the difference in chroma considered to be acceptable. We can see that the tolerances or limits for variations in hue are much more critical than those for chroma. We can demonstrate this for ourselves by plotting a series of color samples in LAB space. Starting with a green standard of medium saturation, we plot a sample that is yellower by 2 delta E units. We then plot a sample that is bluer by 2 delta E units. Next, we plot a sample that has higher chroma of 2 delta E units and a sample that has lower chroma of 2 delta E units. In addition, we plot a sample with an L value that is lighter by 2 delta E units and one that is darker by 2 delta E units. Each of these samples represents the same degree of color difference. But how do they compare on the basis of a visual assessment? Let's take a closer look at 3 of the samples. Which one appears to be the least acceptable match to the standard? To most observers, the choice would be number 3, the sample that's yellower, as the least acceptable match. Looking at the 3 other samples, we can again select the least acceptable match. Number 4, the sample that's bluer, would be the most likely choice as the least acceptable match. Although the 6 samples have the same delta E, the 2 samples which differ in hue appear to be the least acceptable matches to the standard. This is how these 2 samples plot in relation to the standard in LAB space.
While the evaluation of these 6 samples might indicate that LAB space is somewhat more linear from the standpoint of perception when compared to the chromaticity diagram, we see that we still have a problem. The eye puts much more emphasis on differences of hue than it does on differences of chroma and lightness. Fortunately, within this LAB space, we can break out these differences separately and describe them separately, and therefore we can get around the problem.